Hey folks, up until now we've covered decision trees, modeled one tree at a time. A single decision tree is easy to interpret, but it suffers from high variance. Today we'll cover 3 ensemble methods that address this problem: bagging, random forests, and boosting. Let's dive in. Bagging averages predictions from many trees to stabilize the model. Random forests take bagging one step further by decorrelating the trees. And boosting builds trees sequentially, where each new tree learns from the mistakes of the previous ones. Let's start with the problem bagging is designed to solve. Suppose we fit a decision tree to a training set, and then change just a handful of observations and fit another tree. The 2 trees can look completely different. The first tree splits on x1 at the root, while the second splits on x2, and the structures below the root don't match either. This instability means decision trees have high variance. Bagging, short for Bootstrap aggregation, is an ensemble learning technique designed to reduce variance and improve accuracy. The idea is simple: create multiple versions of a model using different training sets, then average their predictions to get a more stable model. It is particularly useful for decision trees. Why does averaging help? Recall from exam P that given a set of n independent observations, z1 through zn, each with variance sigma squared, the variance of their mean is sigma squared divided by n. This equation shows that averaging a set of observations reduces their variance. So by aggregating multiple predictions, we can achieve a more stable and accurate prediction model. The Bootstrap method builds on the idea that averaging reduces variance. First, consider the case where we sample B separate training datasets from the population. We fit a model to each one and average the resulting predictions, f hat 1 of x through f hat b of x. This average yields a low variance model. In practice, however, we usually do not have multiple training sets. Instead, we bootstrap by repeatedly sampling with replacement from a single training set. Here's an example. Our original training set has 9 observations, labeled 1 through 9. From it, we draw 3 bootstrapped samples, each of size 9, by sampling with replacement. Because we sample with replacement, the same observation can appear more than once. In the first bootstrap sample, observation 3 appears twice, while observation 9 doesn't appear at all. Each bootstrap set is then used to train a model, giving us f hat star 1 of x, f hat star 2 of x, and so on, up to f hat star b of x. The final bagged prediction is obtained by averaging all the predictions from the B models. This is the bagging formula, and it mirrors the averaging formula from the ideal case, just with bootstrap models instead of models from separate training sets. Bagging significantly improves predictions for many regression methods, especially decision trees. For regression trees, we grow B unpruned trees on B bootstrap training sets and average their predictions. Each tree has high variance but low bias, and averaging reduces the variance while maintaining the low bias. Bagging is also effective for classification trees. Instead of averaging, each test observation's overall prediction is determined by a majority vote, the class that occurs most frequently among the B predictions. A large number of trees will not lead to overfitting. In practice, B is set at a value where the error has stabilized, such as B equals 100. A nice feature of bagging is that we can reliably estimate the test error without cross-validation or a validation set. Here's the key idea. On average, each bagged tree is fit using about 2/3 of the observations. The remaining 1/3 are not used to build that tree, and they are known as out-of-bag or OOB observations. For tree 1, the highlighted observations are out of bag. Each tree leaves out a different set of observations. Tree 2 has its own out-of-bag set, and so does tree 3. So across all B trees, any given observation is out of bag for roughly 1/3 of them. This gives us around B over 3 predictions for any given observation, each made by a tree that never saw that observation during training. We average those predictions, or take a majority vote for classification, to obtain an overall prediction for each of the n observations. From there, we calculate an overall out-of-bag error to assess model fit. The out-of-bag error is a valid estimate of the test error because the response for each observation is predicted using only the trees that were not fit with that observation. For a sufficiently large B, the OOB error is comparable to the leave one out cross-validation error. And unlike cross-validation, the out-of-bag approach requires no additional model fitting, making it computationally efficient for large data sets. Bagging improves accuracy, but that improvement comes at a cost: interpretability. A single decision tree provides a clear, interpretable structure that shows exactly how decisions are made. But a bagged model combines many trees, and each of those trees may offer a different perspective on which predictors matter. The result is a complex structure where individual decision paths are obscured. To recover some interpretability, record how much each split improves the model. For a regression tree, this is the decrease in residual sum of squares. Here, the colors track which predictor receives credit for each decrease. We then add the decreases credited to each predictor across all splits in all B trees. Finally, divide these totals by B to create an overall variable importance summary. A large average decrease indicates an important predictor because that predictor consistently reduces model error throughout the ensemble. The split criterion depends on the type of tree. Regression trees measure the decrease in residual sum of squares, while classification trees use the decrease in the Gini index. Bagging has a weakness, and random forests are designed to fix it. Suppose the dataset contains one strong predictor, x1. When we bag, most of the Bootstrap trees will use that strong predictor in their top split, so the trees end up looking very similar to each other. When we average predictions from these highly correlated trees, the reduction in variance is not as substantial as it would be if the trees were less correlated. Random forests address this problem by adding a second layer of randomness. In addition to growing each tree on a Bootstrap sample, a random forest considers only a random subset of m predictors at each split. A typical choice is m approximately equal to the square root of p. Here, with 9 predictors, each split considers only 3 randomly chosen predictors. Note that when m equals p, every predictor is considered at every split, which is exactly bagging. So bagging is a special case of a random forest. With this restriction, p minus m over p of the splits will not even consider the strong predictor, giving other predictors a chance to influence the model. The trees become decorrelated. Some split on x3 at the top, some on x1, some on x7. Averaging these decorrelated trees gives a larger reduction in variance. A few practical notes. The choice of m balances bias and variance, and a smaller m is useful when a large number of predictors are correlated. Random forests, where m is less than p, typically lead to a slight improvement over bagging. And just like bagging, using a large number of trees will not cause overfitting. Our last ensemble method is boosting, and it takes a fundamentally different approach. Unlike bagging, where models are built independently on Bootstrap samples, boosting builds models sequentially. Each new tree is fit to the residuals of the current model, so it focuses on the mistakes made by the previous trees and attempts to correct them. Here's the boosting algorithm for a regression tree. Step 1. Initialize the prediction function f hat of x to 0 and set each residual ri equal to the response yi. Step 2. For b from 1 to b, repeat the following. First, fit a regression tree with d splits, giving d plus 1 terminal nodes, to the training data x and the current residuals r. Then, update the prediction function by adding a shrunken version of the new tree, lambda times f hat b of x. Finally, update the residuals by subtracting that same shrunken prediction. Step 3. The final boosted model is the sum over all b trees of lambda times f hat b of x. The parameter lambda is the shrinkage parameter, or learning rate, and it lies between 0 and 1. It controls how much each new tree's predictions influence the overall model. By shrinking each contribution, the model learns slowly, which helps it avoid overfitting. Boosting involves 3 tuning parameters. Let's go through each one. First, the number of trees. B. Unlike bagging in random forest, Boosting can overfit if B is too large, although this overfitting happens slowly. We use cross-validation to select the optimal value of B. Second, the shrinkage parameter lambda. Typical values are 0.01 or 0.001. Keep in mind that a very small lambda slows learning down so much that it can require a larger B to achieve good performance. Third, the interaction depth D, which is the number of splits in each tree. This controls the complexity of each tree in the boosted ensemble. Often, D equals 1 works well, making each tree a stump with a single split. With stumps, the model becomes additive, where the effect of each predictor is considered separately and then summed to form the final prediction. To wrap up, let's visualize what interaction depth means by breaking a full decision tree into stumps. Consider this decision tree. It has 4 internal decision nodes: the root decision, decision 1, decision 2, and decision 3. A single boosted tree with a large interaction depth could capture all of these splits at once. Now suppose we boost with an interaction depth of 1. Each tree is a stump with a single split, so the structure of this full tree is captured by 4 separate stumps. The root decision becomes stump 1, decision 1, becomes stump 2, decision 2, becomes stump 3, and decision 3 becomes stump 4. With stumps, the effect of each predictor on the response is considered separately, and the effects are summed together to form the final prediction. That's what makes the boosted model additive and easy to interpret. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.